Let's define what Laplace transforms are. I'm going to use LT for short to denote Laplace transforms. Laplace transform of a function is defined as an integral of that function multiplied by an exponential function. The integral is between 0 and infinity. The L, calligraphic L here, is the Laplace operator, and once we perform Laplace transform, we get a function in the Laplace domain S. Imagine two domains, one in time, one in Laplace domain. The function f of t using the Laplace operator is transformed to the function capital F of s in the Laplace domain. We can of course perform inverse Laplace transform and go back to the time domain. Capital F of s is the symbol for Laplace transform of small f of t. S is a complex Laplace variable. In the process of going from time domain to Laplace domain, we simply replace the variable t with the complex variable s. But the function itself, f of t, small f and capital F, those two functions are also going to be different. Inverse Laplace transform of f of s would give you the original function back, which is small f of t. It turns out that Laplace transform has some very important properties, one of which is that it is a linear operator. In other words, if you're given any two functions, f of t and g of t, and some constants a and b, Laplace transform of the linear combination of these two functions, f of t and gt, is going to be equal to the linear combination of Laplace transforms of those two functions, respectively. This property of Laplace transforms is what is called superposition principle. We're going to be using this again and again in finding Laplace transforms of complex processes with more than one unit. Now, in order to move ahead, let's first derive Laplace transforms of certain important but simple functions. Let's start with a constant function. A constant function is a function whose value is constant. In this case, I'm assuming it to be a at all values of positive times. Let's also assume that a is greater than or equal to 0. In this case, the function itself can be shown as shown here. It does not matter what the function value is for negative times, because the Laplace transform, by definition, is an integral between 0 and infinity and is only defined for positive values of time. Then, the Laplace transform of the constant function is going to be equal to a over s. And the math here is rather straightforward. So Laplace transform of a constant function a is simply a over s. So from now on, I want you to be able to think in the Laplace domain. By that, what I mean is when we are talking about a constant in time domain, it should immediately occur to you that that constant in Laplace domain is a over s. Let's derive a Laplace transform of a derivative. As I mentioned earlier, derivatives in time domain become algebraic expressions in Laplace domain, and therefore finding the Laplace transform of derivatives is going to be very useful. It turns out that the Laplace transform of the derivative f of df over dt is simply equal to s times capital F of s minus small f of 0. And in the process of deriving this expression, I've used integration by parts, where integral of product of two functions u and v can be expanded as shown here. So the derivative, the Laplace transform of the derivative is s times f of s minus f of 0. The second f is a small f. It's the initial value of the function. And it turns out that if the initial value of the function is 0, then the Laplace transform of the derivative is simply s times f of s. In other words, Laplace transform of the first derivative is a polynomial in s of order 1. You can extend this argument and show using mathematical induction that the nth derivative of any function is a polynomial, is an n-dimensional polynomial in the Laplace variable s. It depends on the initial value of the function and also the initial values of higher order derivatives of the function. Mathematical induction is a standard technique where you show that a particular result is true for n equal to 1 and then prove that it is true for n equal to k, and also it's true for n equal to k plus 1. You prove that if it's true for n equal to k, it's also true for n equal to k plus 1, and therefore you can show that that particular result is going to be valid for any value of n, no matter what it is. Now let's look at the Laplace transform of an exponential function. Laplace transform of exponential functions are also very important because exponential functions appear in the solutions of ordinary differential equations. Laplace transform of e power minus bt, where b is a constant, it has to be independent of time. Notice that the second integral here has an exponential to the power of minus b plus s times t. Now if that power is positive, as shown in the window on the right hand side, if b plus s is minus 2, then the exponential becomes e power 2 times t, which is an integral that is not defined because the integral limits go from 0 to infinity, and as t goes to infinity, e power 2t goes to infinity. Therefore, this integral is only defined as long as the real part of b plus s is greater than 0. And if you assume that that is true, the real part of s is greater than negative of real part of b, then the Laplace transform of an exponential function can be shown to be equal to 1 over s plus b. There are certain standard functions which we're going to encounter again and again. One of those functions is impulse function or Dirac delta function, which is equal to 0 everywhere and is equal to infinity at time 0. Often this impulse function is approximated using a pulse function, and the Laplace transform of the impulse function is 1.
To start off, let's look at the Laplace transform of sinusoids. A sinusoid can be either cosine omega of t or sine omega of t, where omega is the angular frequency in radians per second. The period of these sinusoids is simply 2 pi over omega. We use Euler's identity to quickly evaluate cosine or sine of omega t in terms of the exponential e to the j omega t, where j is simply the square root of negative 1. Since the Laplace transform of an exponential is simply 1 over s plus the constant in front of the exponential, we can easily evaluate the sinusoids using that property. We arrive at the fact that the Laplace transform of a cosine is simply s over s squared plus omega squared, and similarly, by following the same exercise, we find that the Laplace transform of sine is simply equal to omega over s squared plus omega squared. Let's look at the Laplace transform of a time delay now. In a typical process, delay is unavoidable because usually it takes time for mass or energy to transfer from one medium to the next. In this typical example of mass transfer, we have two tanks joined by a pipe. We have arbitrary inlets W1 and W2 and an arbitrary outlet W3. If we monitor W3 and keep W2 constant, we observe that if we introduce an increase in W1, we are likely not going to see an increase in W3 at the exact same time. If we increase W1 at the time T1, we are likely to see an increase in W3 at a later time t2, separated by the difference theta, which is a common symbol used in process control to denote the time delay. Now the time delay, like I said earlier, is unavoidable because of mass transfer and the time required for that to occur. A time domain function typically can be expressed as a product of the original function denoted by ft translated to the right by theta units, and therefore we get ft minus theta. We multiply that by the step function st minus theta, which is simply the original step delayed by theta units, just to ensure that all values of the function before theta is 0. We take the Laplace transform of this delayed function fd of t by separating the two integrals from 0 to theta and theta to infinity. We notice that we must use the change of variables in order to deal with the term t minus theta. The first term in the integral can be expressed as a function of t tilde, the change of variables, and we easily evaluate the Laplace transform to be e to the negative theta s times original Laplace transform f of s. Now let's look at the Laplace transform of an integral, which is denoted by I of t. We evaluate the Laplace transform of this integral by separating the different terms using integration by parts. If we use integration by parts in this particular fashion, we can quickly evaluate Laplace function of an integral by noticing that the first term simply vanishes because of the exponential to an infinity, and also the integral with an upper and lower bound of 0. The second term survives, and this is exactly the Laplace transform of an integral, which is 1 over s times f of s. The partial fraction expansion is very useful because it rewrites the Laplace transform of a very complicated function into a sum or a series of easily invertible Laplace functions. For example, let's look at this very complicated looking fraction here. This is impossible to evaluate directly because we do not have an explicit inverse Laplace transform for this function. Often, the dynamics of a process will result in a Laplace domain expression such as the one above. This is usually in form of a fraction, which is a numerator n of s over the denominator d of s. And this fraction must be proper in the sense that the order of the numerator is smaller than the order of the denominator. For example, the first fraction is proper because of that exact reason, and the second and third functions are improper because the order of the numerator is equal or larger than the order of the denominator. To determine the roots of the denominator function, we simply rewrite d of s in terms of a product of s minus r1 to s minus rn, where r1 to rn are the roots. If the roots are real and distinct, then we can expand the fraction as a constant alpha over the individual terms s plus r1 through s plus rn. Alpha 1 through alpha n are constants, which we can evaluate by first performing the Heaviside expansion. The Heaviside expansion is simply the multiplication of every term in ns over ds by d of s, which is the denominator polynomial. By doing so, we get polynomials with the constants alpha 1 through alpha n in front of them, and we can evaluate these constants by substituting in the roots individually, one at a time. For example, to find the first constant alpha 1, we substitute in the first root s equals r1, and we simply multiply and divide through the appropriate terms. In order to realize why partial fractions are important, let's look at an example of a solution of a third-order differential equation. By using partial fractions and Laplace transforms, we can transform the solution from a differentiation or integration exercise into purely algebraic exercise. And algebra is very easy and simple to manipulate. If we are to solve the following equation, which is d to the third power of y to all the way through the first derivative of y plus 6y equals 1, with several constants in front of them, we realize that this exercise is very difficult by direct integration. However, if we perform Laplace transform and use the principle of superposition on every term, we can quickly separate each of the derivatives. We realize that the initial value of y as well as the initial values of all the derivatives makes the exercise extremely simple because all the terms after the first term, which is Sn times f of s, vanish. And for each derivative, we can simply write it as s to the power of the appropriate derivative times f of s. We can collect the like terms multiplied by y of s and join them on one side. Finally, we can rewrite y of s as the division of 1 over the polynomial. Now let's perform partial fractions on this polynomial. First, we rewrite the denominator polynomial in terms of a product of its roots. The roots in this case are 0, -1, -2, and -3. In the second step, we rewrite the fraction y of s as a sum of easily invertible Laplace functions. We realize that these functions are simply the Laplace transform of a step and exponential functions. In the third step, we multiply through by the denominator polynomial. And we arrive at the following equation where 1 equals the product of alpha 1, alpha 2, alpha 3, and alpha 4 by the corresponding s terms related to the roots of the original denominator polynomial. Finally, we evaluate alpha 1 through alpha 4 by substituting in the roots one at a time. This exercise is completely algebraic, as mentioned before, and it simply takes a very small amount of time to complete. We realize that in every case, all of the terms except for one vanish to 0 because of the corresponding root that causes one of the terms to equal to 0. After we arrive at the solutions of the constants alpha 1 through alpha 4, we can rewrite y of s using the solutions that we just arrived at. And this is easily invertible for the reason mentioned previously, where the Laplace transform and the inverse Laplace transform of a step and exponential are easily converted to one another. For homework, please read the following pages 47 to 48 in the Seaborg and Doyle 3rd edition process control textbook in order to familiarize yourselves with how to perform partial fraction expansions for repeated roots and imaginary roots.